Swayam Prabha. Digital India. Educated India.
So let us start with a positive note. So I hope yesterday you went through that cache lecture by Professor Mainak Chowdhury, though the volume was low, but at least the slides were there. See, that is a type of research that goes into server class architecture, right? What is the difference between a Xeon server or an Intel server or an IBM server and a mobile phone that you are using, or the laptop or the desktop you are using? One of the major differences there is in the cache. So it was just an opening for you. Now I am not going to ask questions from that, of course. It's just an opening for you that so much of effort goes into making a server, and that effort, 90% of that effort, which distinguishes a chip from a server class chip versus a desktop class chip, is basically on the cache hierarchy. Okay, so when you take a course on computer architecture, you would be educated more on that stuff. Okay, so with this, so we will now go into the last part of our course. Okay, we finished Amdahl's law, right? So we will go into the last part of this cache, this discussion on cache, and that is what we call as the shared memory architecture. Okay, we will spend quite a bit of time here because I want to teach you some amount of parallel programming. I also want to cover some amount of issues in building multi-core processors. And as I told you, you will not find a single core chip anywhere. Okay, if you want to buy an 8386 with single core, it will cost you $5,000 because last few pieces, museum, antique value. Okay, it's like a furniture some 200 years old in your house. Okay, so now we have to now see what it means to bring up a multi-core architecture, and also we need to see how to program it. Is there some way by which you could program, right? Many of the university curriculums, in my opinion, none has matured enough to actually educate you on from a background of a multi-core processor. Still we are sticking to the old single core. Our algorithms are again sequential algorithms that we teach. So there needs to be so the technology is much far ahead of what the actual software could be made today, or how the mind actually, a programmer's mind work today. So one important thing that we need to understand here is there is no more sequential programming. If you are going to stick to your sequential programming, we are going to be in a bigger soup. What is that soup? Today I actually suggested this paper long back, I think even the third semester, end of road for conventional microprocessors, right? This is by a group at Texas at Austin University, Doug Berger's team. So they wrote this paper wherein it says that beyond some 3.5 gigahertz frequency, your frequency will not scale. You won't go to a 4 gigahertz Intel processor. I think we did not see an AMD or an Intel processor with 4 gigahertz speed. The reason was that as your frequency increases, there was a huge amount of power surge that was happening, and that's why we stopped. And then what they did was that they gave multi-cores with each 2 gigahertz. Now today I have 4 core each running at 2 gigahertz. So essentially I could get 8 gigahertz, provided I know how to program it. If I run a program which was fine-tuned for a 3.1 gigahertz, 3.5 gigahertz processor, today the same program I run in this machine, it will be much slower. Are you able to follow that? It will be much slower than the what we got as a performance in 2004 or 2006. So today when I want to exploit the computing, essentially that means that I need to know how to use these 4 into 2 gigahertz, 8 gigahertz. How should I get that performance? I should know parallel computing, and that is precisely why we are trying to look at this. Now what is parallel computing after all? Right? I have a job, we have already seen this. Suppose I have 100 numbers to add and I have 4 processors, split it into 25 chunks of 25, make each processor add that 25, and then interact with each other to find out the final answer, right. So there is some computation that is going to go on in your process, individual, we will call it as a core now, individual cores, and then these cores have to talk to each other, share that information to come out with the final answer. And the sharing of information, suppose we 4 are 4 cores, the way by which I exchange information between you and between us is through the memory, and that is why this is called as shared memory architecture. Okay? So I share the memory, the memory is shared with among 4 of us, and whenever I want to communicate something from A to B, or when P1 wants to communicate to P2, it uses the memory. So P1 writes to location 1000, P2 reads from 1000, right. So this is basically the shared memory architecture. So when I want to start doing parallel programming, this is one fundamental thing that we need to agree upon, that we need to share information between the processor some points of time, and the way we share it is through memory. So that gave rise to a computation model. So we have already seen an algebraic model of computation, right, based, you say order n squared means what order n squared? N squared operations, who dictates that operation? There is a model of computation that dictates that operation. I have covered that in many times I have mentioned about this, right. Even in this and data structures, Saritra would have taught you those things. Okay. So now, like how I had a sequential model of computation, I will now have a parallel model of computation. Okay. So I think whatever I have told now is just basically summarized in this slide. Let me just read it out. Sharing one memory space among several processors is what we mean by a shared memory architecture. And the most important thing is that I need to maintain coherence among several copies of a data item. Now I am going to have a cache, right. There is one shared memory, and each of these processors are going to have a cache, correct. And so when I read 1000, that 1000 will belong to me. So there is a version of 1000 in the main memory, and there is also a version of 1000 in my local cache. And for performance reason, I will not have a write through cache, I will have a write back cache. You understand the difference, right? So when I have a write back cache, that means I am going to go and do a lazy write back later. So the value of 1000 that I will have in the processor core in the cache would be different from the value of 1000, the value that will be stored in the actual memory location 1000, and that gives us the cache coherency problem, right. So when we look at shared memory architecture, there are two things which need to know. How are we constructing this shared memory architecture, right? We know how to construct a superscalar out of order processor now, right. How can each of these superscalar processors called a core, how of these cores, say 4 or 5 of them, can be put into the same chip and made to execute a parallel program, right. So that means we have to facilitate some inter-core communication, and that communication will be through the shared memory. Once we establish that model, now we need to have a parallel programming model, and we need to see that it works properly. Okay, so this is, do you understand this? So now we will take two things here. One, we will look at shared memory, how this coherency is going to be handled. That is one part. That's the challenge, right? Now I put 4 cores, each has its own cache, I have a common memory, I have a bus through which each can read and write. Now what is the problem to solve? Coherency. So what is that you need to understand at the second year of your curriculum with respect to understanding multi-core, how cache coherency is solved. If that is understood, that's a big thing. And then the second thing that you need to understand is how to program these machines. Both we will cover in some depth. Okay, so this is the whole stuff here, summarizing what I have done so far. So what I have talked so far. Now there are 4 processors, processor 1, 2, 3 and 4 in red. Each has its own internal registers and each has its own L1 cache. And all of them connect through a common bus, and then there is a memory that is connecting it, right. It is connected to the memory, okay, right. So processor 1 will talk to processor 2 by writing into this memory, and this fellow will read from this memory, okay. there is no direct communication between the cache. This fellow cannot read into this fellow's cache. He can only read his cache and this memory. He can read only his cache and memory. If I could start interchanging between caches, then it becomes a nightmare. Okay, so we can't build an architecture. It's practically infeasible for us to do such a thing, right? Right. So with this, let's see. I have one extra word in this slide. Snoopy. Okay, which everybody likes. I like to snoop. Okay. Now why it is called Snoopy? Can you just guess? I'll give you a couple of minutes. What is Snoopy to do in this slide? See, the point is, when I am trying to read 1000, right? Now some other processor could have the latest value of 1000. So let me say we both are working. So he has read 1000, he has written into 1000. That value of 1000, the latest value will be in his cache, not in the memory. Now I want to read 1000, I don't find 1000 in my cache, so I have to go up and find it, right, to the memory. At that point, he has to somehow come and tell me, hey, don't go to the memory, I am having the latest value of 1000, wait, I will update it, you go and read it from. Correct? Let me again explain. We both are working together, he has read the location 1000, he has brought it into his cache and he has changed the value. Now after that I am trying to read 1000. At that point of time, I don't know whether he has changed his value, it is his internal affair, right? It is between his process CPU and the cache. I don't know what has happened to that 1000. Now when I am trying to read from 1000, somehow this fellow has to stop me saying, hey, wait, I have the latest value of 1000. So don't read, stop. Then he has to update that value of 1000 and then I have to go and read from it. Are you able to follow what I am trying to say? So that means his hardware, after modifying 1000, has to keep snooping into the bus. Is there somebody else trying to read 1000? So I have the latest value of 1000. After I get the latest value of 1000, this his cache controller or whatever, some part of the hardware should be snooping. Snooping means reading what is happening in the bus, what other fellows are doing. That's what we call snooping, right? What's the definition of literal meaning of snooping? What he is doing, right? I am not bothered of whatever. This is RG's base, right? Okay. Relative grading space. It's not just important how well I score, how others score. So, okay, right? So that's what. So we keep snooping on this, and at some point of time we say, okay, if that fellow is going to read 1000 and I have the latest value, so I go and stop him. Okay, so all protocols that enable cache coherency, that solve the problem of cache coherency, in some way or other does snoop. And snoop is the way that we can basically handle cache coherency issues. Okay, right? Is a very practical way by which we can handle cache coherency. We could have some global ways of handling this, but this is much more localized and distributed, and is a very neat way, right? So Snoopy based cache protocol is an area of research. Okay, people have come out with several Snoopy based cache protocol, and that will be actually, if you take a course on computer architecture, you will know much more about this. But we will do one simple Snoopy based cache protocol as a part of this course. Okay, are you able to get what I am trying to say? Right? If you don't follow this, please stop me here, because it's going to become a little more intense as we go down the line. Okay, right. So this is the Snoopy based protocol. So this is what is actually given in many textbooks, and with 1, 2 or 3 paragraphs of explanation, and obviously you will not understand what it means. Okay, and there are two state machines, but you will understand that this is whatever you see here and in the next slide are deterministic finite automation, right? It is a DFA. There are 3 states and many edges that are going between these states. Okay. Okay. Now I will now go back. So just remember this slide. This slide will be something like, after you understand what I teach, this is very nice for revision. So these two slides are good for revision, but not for understanding. Okay. I will teach these two things, one today and probably, if possible today, or today and tomorrow I will teach. Okay, I will split it across 2 classes. Okay. Now we will go back to our famous this. Okay. Good. Okay, now I have 4. So please do. So there are 4 processes. And there is, each has their own cache. And there is a RAM. And they all share a common bus. Correct? They all share a common bus. Now, okay, at any point of time, one of the processor will have control over the bus, or the bus will be allotted to exactly one of the processors. So that we will call that processor as a bus master. So we will have some protocol like what we will learn about this in distributed computing if we take a course, but for very quick understanding, we will have something called a token ring protocol. It is nothing but a token that is circulating. So the token first will be with P1. When it has the token, it becomes the master. After that, it will give to T2. For some time it will be there, it will give to T2, then it will give to T3, then it will give to T4. One by one, this will go like a merry-go-round. Very merry or not merry, I don't know, but it will be going around, round and round. Okay, right? So this is called a token ring, simple token ring protocol. So at any point of time, exactly one fellow will be the bus master. The other fellows will be just watching or snooping. Okay. So at any point of time, one fellow will be doing the transaction, and other fellows will be doing, exactly one will do the transactions, the others will be doing what? Snooping. Like, what is he trying to transact? You got this? Huh? Easy, right? Okay. So every point of time, there will be exactly one fellow will be doing the transaction, others will be seeing what is it he is trying to transact. Okay. So for every memory location in the RAM, there is one line, cache line, in which I can go and recite. For every memory location, there is one cache line in which I can go and recite in every cache, and these are all symmetric multiprocessors. That is why we call it as SMPs. It is not shared memory multiprocessors or symmetric multiprocessors, right? We also call it symmetric multiprocessor. Symmetric means everyone is equally capable of everything, right? If I can do something, he can also do that. If I cannot do something, he cannot also do. So there is no asymmetry between each. So this is symmetric multiprocessor. So everybody will have exactly the same size of cache. So if I have a location 1000, say I have, let me assume that there are 2 locations, say 1000. So let us forget this 1000 business. So I have A1, I may have another address A2. Just for the sake of understanding, let A1 and A2 map onto the same location in the cache, right? When I mean this, let A1 and A2 map onto the same location in the cache. Now, so for every cache line here, right, we had one state in the previous thing. What was the state? It is an invalid line or a valid line, right? Then we had dirty bit, etc. So we have an invalid line or a valid line. Now we will have, that was invalid, valid. So it was a 1 bit, 1 bit thing. Now we will have 3 states. So every cache line inside this will it had 2 states earlier, now it will have 3 states. What are those states? Valid, so first thing invalid, right. Then we will have something called shared, then there is something called exclusive. So we have 3 states here, one is invalid, another is shared, another is exclusive. Okay, right. Now what is invalid? Whatever entry is stored in this cache line is junk. What is shared? I am storing some address here, somebody else also is storing the same address in his cache. For example, A1 maps onto some line, if that line is shared, that means A1 is mapping onto some line, that line is shared means A1 is stored in that location in the cache, there is a version of A1 in the cache, there is also a version of A1 in, there can be also the version of A1 in some other cache of some other processor, and if that is the case, then the value stored here, let me say the value is 11, the value here should also be 11 and the value here should also be 11. So if a location is in shared state, that means for that address, please note it very carefully, for that address I have a value which is the same as the value that is stored in the RAM, and somebody else also could have the same value. Somebody else also could have the same address in their cache and the value will be the same. You understand this? So if a particular cache line in a particular cache is in shared mode, again I repeat, it has a value and that value is the same as what is there in the memory, and some other processor could also potentially have, it is not necessarily it should have, could also potentially have the same address in its own cache with the same value, right. That means my line is in a shared state. Are you getting this? Is it okay? Are you able to follow what I am trying to say? Okay. Now what is the next thing? There is something called exclusive. Exclusive means I alone have, if suppose this is at exclusive state, that means I alone have that address stored in my cache alone, and the value that is there need not necessarily be the value in the main memory. I alone have that address stored in my cache. So if A1 is mapped, A1 is stored in P1's cache with exclusive means the A1, the copy of A1 is exclusively in P1's cache, no other cache could have A1, okay, and the value that I have stored in that cache need not be necessarily the value that is there in the memory, and whatever I have stored is the latest value, okay. So this is what exclusive means, right. To repeat, every cache is symmetric. For every address there is a location in the cache where I can map it to. Now coming to the caches, every cache line can have one of the 3 states. It can be invalid, that means whatever is stored there is junk. It can be in shared state, that means the address that it is storing can be part of some other cache of some other processor also, and the value that is stored in that cache is the same as the value that is stored in the memory, and it is the same as the value that will be stored in the other processor also. That goes by the definition. If the cache line is in exclusive state, then the address that is stored in that, it is the only cache that is storing that address. No other cache of any other processor could store that address, and the value it stores need not necessarily be the value that is stored in the main memory, and this is the latest value of it. If somebody wants to read this address, it has to take it from this cache. Are you getting this? Very clear, right? Should I need to repeat? Please understand that the state of a cache line, the state of a cache line can go between these three. It can be invalid, it can become shared, it can become exclusive, right. And the state of a cache line can be changed because of three things. What is it? Because of a transaction that is initiated by the CPU. I am a cache belonging to P1. The CPU tries, when it is the master, it tries to read and write some memory location, and because of that the status of, I am a cache line, because of that my status can change, and this will happen when P1 is the master, correct. Now when P1 is not the master, something, so I will be snooping, and something that is happening on the bus can come and change my status. So the status of a cache line can be changed because of two things. Number one, when I am P1, I am a master, correct. I will be doing certain transactions to the memory, load and store, and because of that my cache line can change, my state of the cache line can change, right. The other thing is that when I am not the master, I will be snooping on the bus, and because of some transaction over the bus my state can change. So my state change is governed by two state machines. One state machine which is based on the transaction initiated by the processor to which I am associated to, and another change is because of the state machine which is associated with the transactions on the bus. The first state machine comes into effect when when the processor to which I am associated to has the token. The second state machine comes into effect when I do not have the, when the processor to which I am associated to does not have the token. Okay. So that is the two state machines that I showed in the slides. Okay. So that is the two state machines that I showed in the slides. Okay. Fair enough? Are you all able to follow? So what are those state machines? For every cache line, for every status bit, this state machine is going to run. That status bit will be updated based on the state machine. Okay, right?